Hello students, this is Dr. J. Sadiq Basha. So in this file I will see about the heat transfer, lesson number 4. The main contents in this file is heat transfer, and we are going to discuss about the heat transfer concept and types of heat transfer, conduction, convection and radiation, governing equations of heat transfer types, solution of worksheet problem number 10. So first of all, we should know, what is meant by heat. Okay, so can you tell me, anyone can just think of heat? So basically it is a form of energy which has a tendency to move from hotter region to colder region. So the science of heat, okay, which floats from one place to another place, is called a heat transfer. How the heat transfer takes place, in what modes, in what ways. So basically there are three ways. There are conduction and convection, also by radiation. Of course the heat flows only if there is a temperature difference existing between hot region and cold region. So that is a basic concept of heat transfer. You can see a diagram here, considering when you draw when you boil water in a pan, okay, on burning some woods, you can see the flame, the fire will be there from the wood, right? So when it's being burned, the wood is being burned, so it starts to burn it not boil the water in a pan. So the conduction heat transfer, I'll come one by one, starting with conduction, convection and radiation. So conduction heat transfer occurs, okay, from one substance to another substance by direct contact, by direct contact. So how the conduction takes place, in conduction the heat transfer occurs majorly in solids. In solids, the molecules are very closely packed with each other. So since the molecules are tightly closed with the direct contact, so the heated molecules will transfer the heat within the solid material. Of course, when you heat here, so this solid, the pan, it's a solid in nature, so it absorbs the heat from the flame and it gets heated. The pan, the bottom place of the pan is being heated by means of conduction, because the pan is by default it is a solid material. So that heat it gives to the water. How it gives the water? Now water is the another medium, and pan is a solid medium. So the solid medium, once it is receiving the heat from the flame, it gives the heat to the water by means of one more heat transfer, that is called as convection. What is convection? The transfer of heat through a fluid, it could be a liquid or gas, caused by molecular motion. So when you heat the waters, of course, it will be composed of many molecules. The molecules will move here and there, okay, and because of the temperature difference, okay, from the bottom side of the pan and the top layer of the water, so there will be a convection heat transfer. So convection heat transfer, okay, from the bottom of the pan to the liquid, okay, there is convection heat transfer. And what is radiation? Radiation heat transfer, it occurs radiated or transmitted in the form of waves or particles. So when you see the flame, you can when you sit here somewhere here, okay, we can experience some heat waves moving in and around you. So that is because of radiation effect. So the radiation heat transfer majorly occurs in terms of electromagnetic waves, that we are going to discuss in the coming slides. What is the main equation for in this slide? You can see we are going to discuss about conduction heat transfer. What is conduction heat transfer? How it's defined? Okay, what are the materials? Okay, it has high value of conducting heat, and which are the materials having poor conduction of heat? Okay. Now, what is conduction heat transfer? It is a heat transfer occurs majorly in materials by direct contact of matter. By direct contact of matter. So that is conduction heat transfer. So how it happens in solids means because of two reasons, very important. How the heat is conducted in solids, because of two important reasons. One is because of lattice vibration of atoms, due to lattice vibration of atoms, and because of mobility of free electrons. Now you will be wondering what is this lattice vibration of atoms and mobility of electrons, right? So for example, if I have a say a copper, I am going to heat copper metal. Okay, I am going to heat copper metal. I am going to heat somewhere here in one side. Okay, so what happens? Assume the environment temperature here, environment temperature say 30 degrees Celsius. Okay, now when I heat in one side, okay, initially I can hold this copper rod. Okay, I can hold the copper rod, right? But after say 5 minutes or 10 minutes or 20 minutes, okay, I cannot able to hold this copper rod in another end. Why? Because the heat has been transferred from hotter region to colder region. So how, what made the heat to propagate or to displace or to move from one place to another place? Because of the conduction heat transfer. So how the conduction heat transfer has been occurred now? Because if you see the rod here, there will be since rod, okay, it is a copper rod, so there will be the atoms or molecules will be packed with each other, very closely packed with each other. When you heat one atom here, so it gives a heat to the neighboring atom. So the like this the heat will move. I mean the heat will be shared, or heat will be propagated from one atom to another atom by means of vibration of atoms. This is called, this atoms when it's being heated it starts to vibrate. Okay, that is called lattice. Lattice means regular arrangement of atoms. So because of that vibration atoms, the heat is being propagated in solid materials. And one more reason is free electrons. Of course, copper is a metal. So metals basically it will be having a more amount of free electrons. So because of the free electrons availability in the materials, it also plays a very vital role to make the heat to conduct in solids. So this is the main concept of conduction heat transfer. The heat transfer occurs through materials by direct contact. So like that, the atoms are, and another atom is being heat is being shared between one atom and another atom by direct contact of matter. So why? Because of two reasons. One is lattice vibration of atoms and mobility of free electrons. Of course, the metals like copper and aluminum are basically they are considered as good thermal conductors, because they are a good conductor of heat and electricity, and also they are good conduction of heat. I mean good conductors for conduction heat transfer. And opposite in a sense. So some materials are there which are very poor conductor of heat. Okay, they will not having the sufficient amount of vibration of atoms, so it will take more time to propagate the heat or to transfer the heat, okay, within the solid materials. That type of materials called a thermal insulator. Example, wood, okay, glass, plastics, rubber, okay, many stones, okay, rocks. So all those are very poor conductor of heat, because they are very they are not able to conduct heat fast. So they are basically, it's called a thermal insulator. So only heat flows slowly through a plastic, so the temperature of our hand does not rise very much. If you have a plastic stick, something like that, if you heat in one side, okay, you can raise, you can withstand the heat, the hotness very long time. Okay, but if you heat in the copper rod, very soon the heat will transfer, because copper is very good conductor of heat, whereas the plastic is very poor conductor of heat. When you look on this table, you can see the difference. Okay, the values of thermal conductivity. We will see what is thermal conductivity. Thermal conductivity. We will see what is thermal conductivity in the next slide. Materials. See the materials here till for diamond, the copper, the aluminum, steel. Okay, the thermal conductivity is 2000. See, it is very high values. Whereas if you see the non-metals from here, okay, non-metals, the non-metals, the as I said before, so they will having a very poor conduction of heat. So you can see the values of thermal conductivity is very less. Thermal conductivity means what? You can see the unit now. So the amount of heat produced per unit length per unit rise in temperature, that is called as thermal conductivity, right? So this amount of heat production will be more for metals. See here, from steel to diamond, okay, the thermal conductivity is very high. Whereas for rock, glass, wood, for other materials, it is very less. Okay, so that is the meaning of thermal conductivity. Thermal conductivity is one of the important parameter in the conduction heat transfer equation that we will see in next slide. So in this slide, you can see the equation of here, equation of conduction heat transfer. Okay, so what it reveals, so what is the name of the conduction heat transfer? It is called as Fourier's law. It is called as Fourier's law. Okay, Fourier's law, name of Fourier is the name of the scientist. Okay, Fourier means name of the scientist. So what he says that, okay, what is revealed that the heat conduction, okay, depends upon four important parameters. What are they? Thermal conductivity, area of cross section of the particular material, temperature difference dt, temperature difference, and dx, and thickness of the particular material. He says that heat transfer mainly depends upon these four important factors: thermal conductivity, area, temperature difference, and thickness. So this minus has been included because minus, okay, being included here because it means that always heat always moves from hotter region to colder region, so it is a negative sense. So the minus has been included in the formula. So main equation for conduction heat transfer is Fourier's law. So it says that it is the rate of heat conduction mainly depends upon thermal conductivity, area of cross section, temperature difference, and inversely proportional to the thickness. So you can see some examples here for heat conduction. Same thing what I told you before. When you heat, okay, when you heat say a copper rod in a flame, so initially what happens in the sense you can hold the copper rod, okay. After some time the heat will flow gradually towards the cooler region, that is in our hand. So always the heat propagates from hotter region to colder region. Now in this rod, what I told you before, the rods basically is solid in nature. So in the solid, their atoms or molecules are closely packed with each other. So that atoms gets excited and vibrated and shares the heat to a neighboring atom, and thus the heat will propagate from one point to another point. First point. Second point is for the free electrons, because as you know that metals are very good conductors of electricity. Free electrons are very important fact in which the heat is being, current is produced in the metals. So the free electrons also plays very vital role in conduction of heat. In second diagram you can see the same thing. When you one side you are heating and another side is very cool. When you heat in this area, what will happen? So this heated portion will transfer the heat to the cooler region. So when I say this Q here, so length here, length, okay, length is like like thickness. Then heat flow, that is Q here. You can calculate, and area of the cross section, that is your area. And K depends of the material which is being used for the experimentation. K is thermal conductivity, and the unit of thermal conductivity is watts per meter degree Celsius. Just in previous slide we discussed, right? What is thermal conductivity? Amount of heat, W is unit for rate of heat transfer. Okay, so the amount of heat transferred for a material per unit length per unit rise in temperature, that is called as thermal conductivity. So what is the unit of Q? It is watts. Okay, be careful. In previous lessons we discussed the unit of Q as joules, right? Joules or kilojoules, but here I am telling you it is watts. You can ask why side is like that, because it's not Q here. The name of the Q in heat transfer is heat transfer rate. Okay, heat transfer rate is rate of heat transfer. So watts has another unit. Watts is joules by second. Joules by second. Don't confuse with this Q and other Q in the lesson 3 and lesson 2. Okay, because in the lesson 2 we discussed Q as joules. We didn't say it is rate of heat transfer, right? We said that's heat energy stored, heat energy rejected, like that. But in case of heat transfer, we have to tell with respect to its rate of heat transfer. Means rate means what? With respect to time. So joules per second. So Q is joules, but when you say respect to time means then it becomes joules per second or watts. Okay. So be careful with the unit of Q in heat transfer equations. So this is a worksheet problem. Worksheet problem number 10, first problem. The inner surface of the plain brick wall is 60 degrees Celsius and the outer surface 35 degrees Celsius. With the aid of a neat diagram, calculate the rate of heat transfer per meter of surface meter square of surface area of wall, which is 220 millimeter thick. The thermal conductivity of the brick is 0.51 watts per degree Celsius. So this is K, right? Thermal conductivity is denoted as K, and this is thickness L. Okay, L or dx, both are same. Okay, dx. Then this temperature is given. Say this is T2, this is T1. 60 is T1. So suppose if I have a say a plain wall, something like this, a plain wall. Okay. And considering the temperature in one side is 65 here, 60, and this side is say 35 degrees Celsius. Okay, and the thermal conductivity of this plain wall, the K is given, here, and the thickness of the wall, is how much? 220 millimeter. Okay, this is the problem. So now 60 is greater than that of 35. This left hand side is high, the temperature is high, and of course the heat will flow from 60 to 35. So heat will flow like this, right? So heat will flow like this. So I can tell 60 as T1 and 35 as T2. Okay, so of course we are going to solve this problem by means of conduction heat transform. That's now we discuss Q is equal to minus Ka dt by dx. The unit is watts. So minus K. Okay, the minus I wrote here. So K is given as 0.51. Area we don't know. T1 we know 60 and T2 is 35. And dx is thickness, which is 220 millimeter. That I have to convert to millimeter to meter divided by 1000. Then you substitute these values. Okay, actually the question is calculate the rate of heat transfer per meter square, means per surface area. So you have to find Q per meter square, so per area. So bring this area below the Q, bring this area below the Q. So you will get Q is equal to minus 0.5 to this value. Then the answer Q by answer is 57.95 watts by meter square. Why it's watts meter square? Because Q by A. Q is for watts, area is for meter square. So watts by meter square. This is one of the simple problem in conduction heat transfer equation. Then we will discuss about this convection. The convection heat transfer, okay, majorly occurs between liquids and gases. In conduction, we discussed that conduction is majorly occurs in solids, right? But in convection, the heat transfer occurs majorly in liquids and gases. So for example, consider this diagram now. So when you heat the water, okay, in the pan, this hot water layer in the bottom, it will get heated and it will transfer the heat slowly to the upper layer, right? The upper layer, it will be atmospheric, right? It will be atmospheric, plus the upper layer water will be less temperature than that of the bottom, right? So this water which is in the bottom side, so it will transfer the heat continuously. So how it being transferred from the hot layer to another cold layer? Because of the convection heat transfer. So it majorly occurs, okay, in liquids and gases. And the main equation, okay, the main equation here for convection heat transfer is called as the name equation is Newton's law of cooling. Okay, in conduction I told you Fourier. Okay, in convection the name is Newton's law of Newton is name of the scientist again. So what he says that the rate of heat transfer, again we have to tell rate of heat transfer, don't say heat energy. Okay, so in heat transfer we have to tell the Q as rate of heat transfer or heat transfer rate. Okay, And he says that the heat transfer majorly depends upon two three important parameters. What are the heat transfer coefficient? H here, H is heat transfer coefficient. AS is the surface area of this pan, the surface area, how in which the pan, the heat is being conducted, okay, in particular area, that is called surface area meter square. And Ts minus Tf. Ts is temperature of the surface minus temperature of the fluid, two different temperatures, okay. So that is the concept of Newton's law of cooling. So in Newton's law of cooling, the formula is given as Q is equal to HEAS Ts minus Tf. H is heat transfer coefficient. Here heat transfer coefficient means, again we can tell what we can define easily what is heat transfer coefficient, since the unit is watts by meter square degree Celsius. So I can tell the amount of heat produced per unit area of cross section per unit rise in temperature. That is called as heat transfer coefficient in a convection heat transfer. Okay, and temperature of Ts temperature source, Tf fuel, and A surface area. Okay, surface area of the contact. So this is your Newton's law of cooling. Newton's law of cooling majorly occurs in liquids and gases. Again, there are two types of convection heat transfer. What are they? First type is free. Okay, first type is free or natural convection. Another type is called as forced. Another type is called as forced convection. Okay, so there are two types of convection heat transfer. Okay, what are they? Free and forced. So I am just going to explain using this simple diagrams. Assume this is a hot plate is there. That hot plate temperature is 150 degrees Celsius, and assume the surrounding temperature is 30 degree Celsius. Okay, now assume it is being exposed to this air, okay, to the temperature of 30 degree Celsius. So what will happen after some time? Maybe say after 1 hour. Okay, after 1 hour, what will happen? This hot plate will lose the heat very slowly, okay, and freely, okay, so that this hot plate temperature will reach 30 degree Celsius. So the heat transfer rate from the hot plate to the surroundings will take place very slowly. That type of heat transfer, it is called as free or natural convection. Okay. In second case, you can see the another type of heat transfer, that is called as forced convection. Forced convection heat transfer. In forced convection heat transfer, there should be some external equipment like blower, fan, or compressor, something like that. So when we have that type of setup, so this blower, for example, what is use of blower? Blower is a device which is used to blow the air with high velocity. Blow the air with high velocity. So consider same hot plate here, say 150 degree Celsius here, and say the surrounding temperature say 30 degree Celsius. When you have a blower in one side, so what will happen if you blow the air at the high velocity? Blow with high velocity, more this heat transfer will be very fast. Very fast, this heat will be transferred to the surroundings, and very soon, within say, for example, say within 10 minutes, this hot plate will lose the heat very fast, and it reach the temperature of the surroundings. Okay, this type of convection, it is called as force, means we are forcing the air at the high velocity to make the system to lose the heat very fast. That type of convection, it is called as forced convection. In case of free convection, that the time taken was around 1 hour, for example, right? But in forced convection, maybe within 10 minutes, we can lose the heat of 1 degree Celsius to 30 degree Celsius very fast. So this is the basic types of convection heat transfer. Of course, if you come to year number 4, okay, in year number 4, so there will be one subject with heat transfer with more formulas. But as of thermodynamics, as of you in second year, so this is enough for the subject. Okay. So let us see the problem here. A simple problem with the convection heat transfer. So a wire of 1.5 millimeter diameter and 150 millimeter long is submerged in atmospheric pressure, and electric current is being passed through the wire and is increased until the water boils at 100 degrees Celsius. Under the condition, what is the heat we have to find out? Here convection heat transfer is given. Okay, 4500. That is what? H. Okay, find how much electric power is supplied. This we have to find Q. Okay, rate of heat transfer, and temperature is given. Okay, so here this is 120, it is given vice of temperature. Fluid temperature is given, say 100, Okay, area is the area of the wire. What is the area of the wire? It is pi, okay, dl. So pi multiplied into diameter of the wire and length. So I have to convert to in the meter. So substitute here. So the diameter is being converted to meter and length is converted to meter and pi is a constant and h is given as 4500, right? So substitute here and 120 100 and we'll get the answer 63.5 watts. Okay, so this is the thing. So actually what happens here in a beaker, in a pan or in a container, when electric wire is being submerged in water, okay, it is being submerged. When you apply the current, the wire will be heated. So the wire will be, okay, kept as temperature of 120 degree Celsius and the water temperature will be 100 degree Celsius. So at this point, what is the heat transfer? That is the question. So you can use the Newton's law of cooling using the conversion heat transfer formula and you can find the value of Q. So last type is radiation heat transfer. So it is very interesting, very simple thing. In radiation transfer, the main formula, it is called as Stefan Boltzmann. Again, Stefan Boltzmann is the name of the scientist, so who formulated this equation. What is this one? Radiation transfer. When two bodies are kept at different temperatures, separated by distance, the heat transfer between them is called as radiation heat transfer. Okay, for example, say sun and earth. Okay, the sun temperature will be around 10,000 of 20,000 degrees Celsius, 10,000 20,000 degree Celsius. If you see the global, global temperature of earth, it will be around 22 or 20 degrees Celsius. Okay, so now we are receiving the solar radiations, okay, from sun to earth. Why? Because the sun is at very high temperature and earth is at lower temperature. So because of temperature difference between them, okay, we are getting the radiation in terms of electromagnetic waves. This is called electromagnetic waves. Electromagnetic waves. Electromagnetic waves. So because this fact, the heat is being reached from sun to earth by means of radiation. So what is the formula given here? So Q is equal to emissivity. Q is equal to emissivity. Okay, emissivity means it's a constant. Okay, for a particular material. Then sigma is, it's a constant. So it is a constant of Stefan Boltzmann, name of the scientist itself. So its constant value is 5.67 10 power minus 8 watts by meter square Kelvin to the power 4. Okay, so this is a constant value. You have to remember this value. Don't ask me in the exam, okay, mister, what is the value of this one? So you must remember. It's very easy to remember. 5, 6, 7, 8. Okay, like that. Try to remember 5, 6, 7, 8. 5.67 and power minus 8. So unit watts per meter square Kelvin to the power 4. So it is multiplied with the area. Of course, the area of the surfaces. Then temperature. Temperature of a hot body. T2 temperature of the cold body. For example, say this is sun temperature and say this is earth temperature. Okay, so like that we can assume. So the sun temperature will be very high, T1 will be always high, T2 will be less. Power 4, don't forget to write this power. Power is important. And T1 should be in Kelvin. Radiation heat transfer, please make a note of it. The temperature should be expressed in Kelvin, not in Celsius. You can ask me why. Why, sir, only radiation the temperature should become? Why? Because you can easily see this sigma is in Kelvin. Okay, the constant is, the scientist has already been found the sigma values in Kelvin. So so the temperature, if it is given temperature is given in Celsius, you must convert Celsius to Kelvin. Okay, then only you will get the correct answer for Q. Okay, so this is about the radiation transfer. So basically radiation transfer occurs when there is a temperature difference between two different bodies and there is a distance, and the radiation will be happened because of the electromagnetic waves. Okay, this is a radiation heat transfer topic. Radiation heat transfer problem. What is this? A surface having area of 1.5 meter square and maintain 300 degrees Celsius. Then another body 40 degrees. So this is T1. Okay, this is T1. This is T2. Please convert this 300 to Kelvin. Okay, so add plus 273 plus add 273. Okay, 273 here, 273 here, also add 273 here, also add plus 273. Okay, so now we know T1, you know T2. The value of shape factor due to the geometric location and the emissivity is given as 0.02. This is 0.52 is given, and determine heat loss by radiation. So sigma you have to remember. So sigma is constant. Okay, 5.67 into 10 power minus 8. So this is given 0.52 and area is given 1.5, and this temperature has been converted to Kelvin power 4, and this is also converted to 10 power 4. So when you use your calculator, you will get this answer. This is a very simple problem in the heat transfer equation. Okay, thank you.